Vice Chancellor for Research and Interim Vice Chancellor for Academic Affairs at the University of Hawaii at Manoa. Prior to this appointment, he was the Dean of the School of Engineering and Science and Professor of Ocean Engineering at Stevens Institute of Technology, Hoboken, New Jersey. Dr. Bruno is a visiting professor in mechanical engineering at the University College in London. His research and teaching interests include ocean observation systems, coastal hazards, and community resilience. He is the author of more than 100 technical publications in various aspects of these fields. He has served on numerous advisory committees and boards, including chairing the Marine Board of the National Academies and the Naval Research Advisory Committee to the Secretary of the Navy. Dr. Bruno holds a BS degree in civil engineering from the New Jersey Institute of Technology, an MS degree in civil engineering from the University of California at Berkeley, and a PhD degree in civil and ocean engineering from the Massachusetts Institute of Technology and the Woods Hole Oceanographic Institution. Michael is a fellow of the Explorers Club and our club. He's been a member in National since 2002. He has a book coming out soon on which tonight's talk is based. Let's welcome Dr. Michael Bruno.
This is the first time kind of trying to build a talk around this book. And I'm intentionally titling it Planning for the Expected and Unexpected, and I hope that comes out wise. This is the book that's coming out, The Interaction of Cities with Water, and that is Miami Beach. It was funny, without any prompting, Cambridge University Press art people came up with that. And I was like, wait, is that Miami? And they picked the one place on earth where by every measure, every time anybody takes a look at what is the most vulnerable place on earth in terms of both the risk or probability of an extreme event. So this talk is really about change and a couple of different sorts of changes that are coming together and that we really as a society need to come to grips with and begin to act on now. And I begin with this. I love this map from 1912. This shows the trade routes, 1912. It is a combination of steamship and sailing ships. And what's cool is you take a look at the cities. So of course, New York is there and Shanghai is there. But then there's all these other cities that really you would never have considered to be major trade routes, particularly today. So Liverpool is not on anybody's list anymore. Those moved over to Northern Europe, Rotterdam, and the like. A lot has changed over the last 100 years in terms of who we trade with and where we trade to. And a lot has changed with the climate. This is what has happened in the oceans in the period from 1901 till 2015. So the baseline is 1901 to 1960. What was the average surface temperature of the world's oceans? In the period that followed, 1986 to 2015, that 30-year period, what was the average of the surface temperature of the world's ocean? And this is the two overlaid on one another. And you can see that in comparison, between 1 and 2 degrees Fahrenheit warmer. With some areas, particularly the northern high latitudes, being particularly warmer, 2 to 2.5 degrees, and some hot spots, 3 degrees warmer. Next. And sea level rise by many, many different factors. Sea level rise is occurring. We have large error bars. You see those vertical lines on the dots back to 1870 or so. That's because we didn't have very good records around the globe. These were mostly taken from tide gauges, long-term averages of tide gauges. So you see those errors really very large in the 1800s, and then gradually as you got to the 1940s, 1950s, they kind of squeezed down. They are more believable as data, and then you come up to those solid lines, the blue line, with advanced tide gauge. So now in around 1960, those records are more believable. You see some ups and downs and ups and downs, and then we get up to the top right corner. Now you're measuring with satellites. So that's the first time we can really get synoptic, across the globe, measurements from a relative position in space as opposed to land. The difficulty is the land is often moving, either by glacial rebound in areas like Alaska where the glaciers are going and boom, the land rebounds, or in areas like Louisiana where people are removing water and oil and the land is subsiding, but the land is often moving. When you're measuring from space, you have none of that complexity. And so we believe that data most of all, and that's the inset on the lower right corner. That is the period only with satellite data, and that indicates globally average 3.5 millimeters per year, or 1.5 inches per decade. That seems like a small number, but that's a globally average number. The reality is that these numbers change dramatically depending on where you are. I'll just point out quickly, here closest to me, Alaska is going down by 5 millimeters per year on average. Now that's because of the effect of, among other things, glacial rebound. So these are measurements of the water level versus the land. So if you're a homeowner on the coast, these are an indication of how close the water is getting to you. Forget about what's happening versus space. All you care about is my house going to get wet, right? So if the land is lowering and the sea level is rising, now you have real problems. So if you look at the Gulf Coast, 5 to 10 millimeters per year. Now 10 millimeters per year, 10 centimeters per decade. Now you're talking 4 inches per decade. And now you start noticing things. And we're already noticing things here in Honolulu. You do notice that at the king tides, particularly if it rains, the water doesn't drain from the roads out in front of the zoo and out along the road, because the water level is higher than it was when those storm drains were designed and installed. And so you don't have the pressure. Water wants to flow downhill, not uphill. So there's no more downhill when the tides are high. And that is happening more often, not just here. Here it happens at those extreme tides. In Norfolk, Virginia, it happens at every spring tide. So twice a month, things go underwater, like garages, first levels of garages, parking areas. They invented a new word there because sea level rise wasn't allowed, particularly in legal documents, but in state documents. So they came up with nuisance flooding. So that's called, even in the media, nuisance flooding. Twice a month, your parking lot goes underwater. That's nuisance flooding. But you see, the point of this is that there's a lot of variability. That variability, again, we're only talking data here. That variability can be confusing to people, and I think as scientists we bear the primary responsibility for not having done this well over the last couple of decades and needing to do it better as we go forward, and only basing our discussions on actual data, explain the data, and the variability as you see here. I love this chart. It's a bit of an eye chart, but I think it's super important. I think this paper in Nature will go down as really a seminal paper in environmental studies. It's a group of about 20 authors, co-authors. They defined a term called planetary boundaries. So these are boundaries beyond which human life, human existence could be threatened. And they came up with boundaries for things like, as you see here, climate change, freshwater use, ozone depletion, ocean acidification, pH going up because there's more carbon going into the ocean, genetic diversity, so that's what they call biosphere integrity. There are only 2 things on this, surprisingly for a lot of people, only 2 things that exceed the planetary boundary. The input of nitrogen and phosphorus into our environment, that's mostly from fertilizer, and genetic diversity, that's through species extinction. And the earth and our ecosystems and the things that live in those ecosystems becoming less diverse. Many of these things surprise people when you look at freshwater use, for example, way below, so way in the green, well in the safe zone, what they call the safe zone. Climate change, still yellow. Land system change, this is paving over grass, taking forests and converting forests into agriculture land. So dramatically altering the land cover and the land use. That's what that is. But still, that's only in the yellow. And I say only. There are several that still are not quite understood. Atmospheric loading of aerosols, not just greenhouse gases, fossil fuels, but other releases. Novel entities are the things that we create. So genetically modified crops, and perhaps in the future even animals that have been modified, perhaps to suit a purpose, getting rid of pests, etc. So those are not well understood right now. So that's why that has a question mark on it. I said there were a couple of factors related to change that are coming together to produce a particularly worrisome period in our existence, in my view. One is the changes to the climate and the ecosystem. Some have been natural, others, many have been because of human influence. But at the same time, our population is becoming more and more urban. People are moving to cities. They're moving to cities because of the opportunities that cities provide, right? Particularly for jobs. Well, think back to the 1912 map. People have been moving to coastal cities, settling on the ocean for millennium, right? For obvious reasons. The coast is where you trade from, right? Your port cities are always located on the coast. The coast is typically an area where you have better climate, so you have better living conditions, more possible and stronger agriculture, better quality of life on the coast. So it's not surprising if I told you that most of the world's megacities are located on the coast. What's striking when we looked into this is in 1990 there were only 10 megacities in the world, defined as cities having a population more than 10 million people. By 2017, the end of last year, there were 37. Think about that. 27 years from 10 to 37, and of those 37, 24 are located on the ocean, in harm's way from all of the things that we've been discussing so far, all of this change, and hazards. So now we'll switch gears and talk a bit about hazards. Before we do this, my wife always teases me that I can't help but fall in love with this next slide. Go ahead. I just love this slide. So this is a photo, a photo that is a synoptic view of the Earth at night on the exact same time at night. So when all these people turn down their lights. And to me, it's so striking, except for the US Midwest and a few other locations, those lights are really only along the coast. They're all these populations are clustered close to the ocean. Next. Like we are. All those complexities come together, even the Pacific Islands. Under President Bush Sr., 1990, there was an act passed Congress and he signed called the Global Change Research Act, way back in 1990. And it required federal agencies to come together approximately every 4 to 5 years and prepare a state of the climate report. The next one is coming out in about 2 months. And we had several UH professors, are authors of that report, co-authors. So this is the Pacific Islands region and what we can expect or what we are observing in terms of climate change. I'll point out only a few things here. You can read that, I'm sure, but closest to me over here on the left is ocean heat content rising. For me and a lot of other weather scientists, oceanographers, that is the key. The ocean has forever been the buffer for us. It's not only been where we go and collect our fish and more our natural resources, including fossil fuels. It's probably where we're going to get most of our medicines going forward. But it's where we've put all of our stuff, whether it's fertilizer or pollutants or plastics. It all ends up in the ocean. And the heat that we've been releasing all ends up in the ocean. It turns out that the ocean is just this great absorber of bad things. I had a professor who used to say the solution to pollution is dilution. And I guess way back when somebody decided, well, it's such a vast ocean. Surely it could absorb all the plastics that we've been putting in there since the 1950s in our throwaway society. But it can't. And in particular, the heat content is something that we worry about, because all that heat goes into the great ocean currents like the Gulf Stream, and it goes up north, and then it gets very, very cold, and then it sinks into a bottom current that takes decades and decades to find its way back down to to Antarctica and start its journey back up, eventually rejoining the Gulf Stream, coming up. This is what we call the Great Conveyor Belt. And it takes centuries for the water to come around. And so there are a lot of scientists who worry, are there signatures of what we've done that will eventually come back up and make themselves visible to us? We know that sea surface temperature is rising. We know that hurricanes get their energy from sea surface temperature. The hotter the temperature, the warmer the surface water, the more likely storms will grow, and the more likely they will grow into large hurricanes. Another thing I'll mention, the water. We have an item over there on regarding base stream flow. There are other complexities, I think, that since this was done, were not really clearly understood, but as sea level rises, the level of the groundwater goes up, and as the level of the groundwater goes up, that means particularly along the coast, if it rains a lot, the ground gets really wet much faster, and it stops being able to absorb infiltration, and so now the water ponds, the water doesn't go away, and you get flooding, much more frequent flooding. So it's kind of almost a tertiary effect of all of this that is not plainly evident at first. Next. And we know over the last month, this was wreaking havoc on the beginning of the semester at UH, as these guys know. So in early August, we had our first near miss. They are beautiful things, aren't they, hurricanes? As long as they stay away. Next. And then we had Lane, was a monster hurricane. Lane was a monster. A Cat 5 and a strong Cat 4, just spinning there just south of the Big Island. Next. And then we once again saw the power of those mountains. Mauna Loa, Mauna Kea started tearing Lane apart. And when the trades picked up a little bit and the wind shear came in, that's the remnant of Lane. But still, Lane dumped nearly 6 feet of water on the Big Island in parts. The highest recorded rainfall in the U.S. since 1950. So just an extraordinary event on the Big Island. A faculty member at UH, Professor Chung, who models extreme events and is really one of the world's foremost authorities, particularly in tropical cyclones and in tsunamis. Gary asked me to focus a little bit on our home, and so I worked with him, and he pulled out some of his very recent, this is 2018 result. What he did with his team of students and some other faculty, look up on the left, he modeled Iniki. So this is what we call a synthetic storm. He modeled Iniki as if Iniki took a right turn prior to getting over to Kauai. So what would have happened if Iniki cleared the Big Island and made an abrupt turn and went straight over Oahu? This is a blow-up of what happens on Oahu, and check out the Alawai. Check out the Alawai and the area around the Alawai, and look at the bottom. That's in meters, color-coded. That's anywhere from 6 feet to 8 feet water depth in that hurricane. An even bigger concern is tsunamis, and we've all seen the photos of what happened in the Tohoku tsunami in Japan in 2011. Despite a seawall, that's an enormous seawall that I'm sure everybody in that region thought could never possibly be overtopped, and the destruction. We live in the most seismic area of the planet, the so-called Ring of Fire. So these are the locations of earthquakes from 1900 to 2017, all of them having a magnitude of at least 7.0 on the Richter scale. And you see the clusters, a couple notable clusters for us. Look at South America, focus around the area of Chile, and the west coast, northwest coast of South America, very problematic area for us. We've already had some tsunamis originating from earthquakes on that side. But even more worrisome for us, according to all the experts, is the Aleutians, right from Alaska straight across, and all of the events that had scale higher than 7.0. So Professor Chung and his team modeled what would happen with a major earthquake in the Aleutians. And this was a real eye-opener, particularly because of the almost lack of directionality in terms of impact. So imagine this is a train of waves. You know, you can think about even in your bathtub, you know, just doing this and seeing the waves radiate out from your hand as you disturb the water. Essentially the same thing is happening. And with an underground earthquake, you've displaced the ocean floor by some amount, and that's going to create a bump essentially at the surface of the ocean, which is essentially the beginning of a wave. You have a series of those waves, and they travel very long distances at very high speed, unaffected. They don't feel the presence of the bottom. They are moving faster than a jetliner. That's 4 hours after a 9.6 earthquake in the Aleutians. We've had earthquakes of that magnitude around the world, including the Japanese earthquake. So these are earthquakes that can happen, and 4 hours later, they reach our islands next. I just want you to focus on the left side. So these are what we call run-up. This is, just think about, this is how high the land gets wet. So even on a slope of a mountain, you know, the wave comes in and rushes up. In Alaska and Japan, the highest run-up, just to give you some scale, was 130 to 140 feet. Imagine. So this is saying that here in Hawaii, we would have, look at the top left, that's 40 meters. That's 130 feet. This is more illustrative, I think. So down below, you can see Honolulu. And look at the color code. In terms of the wave height, you're looking at 2 to 5 meters. In a few areas, 5 to 10 meters. So 6 to 15 feet in some areas, and in some areas between 15 and 30 feet along the South Shore. You see the colors there. On the North Shore, you even have some that are more than 20 meters, so that's more than 65 feet. That's all along the North Shore. So Waimea Bay and other areas in the North Shore are very, very exposed. And part of this is because of that topography, because the waves come in and they wrap around a point, just like waves, like surfers know that waves will break around a point. Next. So, I've got to change the tune and get a little more optimistic here. So I'm an engineer, and I've been working on something we call resilience engineering for a number of years, really accelerated after Hurricane Sandy in New York, when the president started a competition, Rebuild by Design, where we were talking about, can we design for resilience? Can we make communities more resilient to the inevitable hazard that's going to occur? Next. Sandy was a big storm. Even though it was only a Category 1, the size, the direction, speed produced the highest storm surge in the recorded history of Manhattan. So going back into the mid-1700s, the water had never gotten that high. So most of Manhattan was dark for almost 7 days. All of the tunnels flooded up to the ceiling. Many of the subway stations flooded. On the shore, this is from Jersey Shore, barrier islands were breached. The ocean met the bay and houses were washed into the bay. And what did we learn? We learned the difference between well-constructed, well-designed buildings. Can you imagine the sand went down that much? And poorly designed buildings. Dramatic differences all along both the South Shore of Long Island and the Jersey Shore. Next. We also learned that you can mimic nature and do a pretty good job of protecting people. So beaches, in a sense, in terms of their natural protective feature, and they would normally be protecting bays and wetlands, they are meant to erode. That's their function. We think of them as being places we put our blanket, but they're really meant to erode. They are natural protective features. So in areas where we no longer have beaches, can we go in there, put sand, preferably sand that is identical to the naturally occurring sand, and that's what you see there in the middle of the photo. There are dredges at work offshore pumping sand up onto the beach. Next. So you end up with a bump in your beach that's 1.5 miles long or so. That's after the project was completed, and it was only some months before Hurricane Sandy. Next. So what happened in Hurricane Sandy, that arrow is pointing at the same place. Of course, the beach all eroded back, but in doing so, totally protected that town behind it. None of the houses experienced damage, whereas other communities had 100% structural damage. And so we learn from nature. Other examples are the way that nature stores stormwater in things like lakes and ponds, and we remove things like that. So we're always talking in some of these, the Abupuahas, including Manoa Valley, can we mimic nature instead of worrying so much about torrential floods, rains and then floods coming down? Can we think about natural detention systems that look like parks? The Dutch are doing this right now, and they're weaving their systems into the natural landscape, so people don't even notice that that soccer field is actually meant to collect water during a major storm. So some very clever design out there. Next. I love this quote from Mayor Bloomberg. We adopted it and said, well, that's right, and you can't learn any of what we've been talking about unless you have data. And to get data, you need to go out there in the ocean, and you need to monitor things for a very long time. So there's this awesome program under the auspices of the United Nations where we, the US, primary participants, France, Japan, the United Kingdom, Germany, Brazil, have deployed for years sensors all around the planet. Many of these are fixed sensors, others are drifters that are out there drifting and telemetering data. The red ones are ship-based measurements. Those obviously move with the ships, but that's a point in time from late last year. That's just to give you a sense of the effort that is underway to understand a lot of what we're talking about. And it's an international effort, as it should be. So building resilience. What is resilience next? So resilience really, for me, is the ability of a community to respond to a major event, to learn from that major event, and to adapt. And by adapting, making that society, making that community more resilient, and maybe even functioning better than it did prior to the event. I know that sounds like really optimistic, wishful thinking, but I don't think it is. I think if we adopted this approach and looked at our infrastructure in different ways, we could, and a lot of this also dovetails with sustainability. If we did not have a reliance or over-reliance on a fragile electric grid, if we had more microgrids, if we had individuals on maybe more solar power. Of course, we're doing a lot of that here in Hawaii. Puerto Rico and Maria, obviously still coming back, but there are plans to re-engineer the grid in Puerto Rico and employ the concept of microgrids to make them that community more resilient to future hurricanes, because there will be another hurricane. Maybe not Maria, that she was historic, but there will be other hurricanes. But the point is, by doing that, you have a better functioning community. You don't have the blackouts. You have more dependable, probably even cheaper energy. Next. So this is pretty much my last slide. In Sandy, in Japan, in the tsunami and the nuclear meltdown, there were lessons that really need to stay learned. One is that it's all about people. I attended a talk by one of the 11 who stayed to gracefully shut down the nuclear reactors at Fukushima. They all thought they were not coming back, so they all took turns taking photos of each other and sending them to their loved ones. And he began his talk with a photo of himself in that moment when they thought they weren't coming back. They all survived, and he ended his talk and he said, "I am more convinced than ever that people are the source of resilience." And so I thought that was quite a dramatic lesson learned. We learned that in New York. Bloomberg and others, the MTA, decided they would pay their people to sleep. The critical workers didn't go home. They stayed in the subway areas, they stayed at the airports, and they paid them for 24 hours each day that they stayed. And those people got the systems working as soon as the hurricane moved on. Uncertainty, a lot of what I've been talking about, I've tried to focus on data, but it's inevitable that there's uncertainty about what's going to happen in the future. We need to understand it, and as scientists, I think we need to convey it. Complexity, we weren't even, in Hurricane Sandy, the power went out. Well, the power went out, so all those gas stations that had fuel for the generators that everybody had couldn't pump fuel because the power was out. And you couldn't get fuel across bridges to deliver directly because the federal government prohibited fuel trucks from going through things like the tunnels. Risk increasingly shared globalization, whether you're talking about shared assets or connected airports, etc., food chains that go across nations. Again, it's all about people. Next is my last slide. 100 Resilient Cities program, you may have heard about it. The Rockefeller Foundation came up with $100 million soon after Hurricane Sandy. They're giving $1 million to 100 cities around the earth to create a more resilient community. Honolulu was among the recipients. They had to compete. New York was among the recipients. Notably, half of them, 50 of those cities, are located on the ocean. So there's another recognition. And with that, next one, I end with a really pretty picture.